All right, now let's get talking about the method of moments and what exactly that means. Now, we're not going to really go too deep into the method of moments per se. What we're going to do is kind of a special instance of the method of moments known as the point matching method. What you can think of as the method of moments is kind of a generalization of that idea to more complicated scenarios. But the basic principle is more or less the same, which we're going to cover here. So we know that this is a really kind of nasty expression. I want to know what this function is. I know what this is at all the points on top of this wire here. And I know the information that sort of relates how this here creates that there. So that's all well and good. So what can we do? So remember in our last lesson, we did this idea of inversion methods, where if I had a finite system of equations with a bunch of n equations and n unknowns, I could use that to create a matrix vector equation and invert it and essentially calculate the charges at discrete points. All we're going to do is kind of that same idea, but we're going to force this expression here to fit that template in some sense. So the first thing we have to do is look at this lambda here and say, this is something we don't really know what it is, but we can at least create an arbitrary approximation to this expression here. So suppose I wrote something like the following. Lambda hat of x prime is approximately lambda of x prime like this. So I don't necessarily have the ability to calculate this thing exactly, but what if I had some crude approximation to it that was at least good enough, all right? And we're going to write this as an expansion of what are called basis functions. So I'm going to write n equals 1 to n alpha sub n times u sub n of x prime, like so. So this is called an expansion coefficient, and this is called a basis function over here. Basis function, and I guess you could call it a basis coefficient, or you could call it an expansion coefficient. Yeah, expansion coef, like that. Okay, that's this thing here, and then we have this thing over here. So how does that work? Well, you can think of this as sort of like an interpolation function that really closely mimics this thing over here. So let's do like some examples, all right? What we're gonna do is imagine taking this continuous wire and chopping it up into tiny, tiny little manageable chunks. So for example, what if I were to say, instead of this continuous charge distribution, what if there was a point charge here and a point charge here and a point charge here, all right, all the way out to the end. So that would be basically taking this continuous charge density, this linear charge density, and approximating it as little discrete point charges here. So if I were to do that, then you could simply say something like this u sub n would be x minus x sub n prime in a delta function. All right, so you imagine all this little section here, all the charge here got squished down into a tiny little point, and I would just calculate those individual point charges here. In which case, this alpha would just be essentially the Q1, Q2, all the way out to Qn like that. And so then I could create a pretty good approximation to what the charges are doing by representing this as a bunch of little point charges. But the beauty of the method of moments is there's a number of different ways to go about that. That's just one way to do it. What we're going to do is kind of take it one step more into the abstract. And instead of squishing them down into tiny little points, I'm going to say, what if I assume that the charge density here, that linear charge density, is a constant value across this little point here. So it might be constant like that, and then it'll be a constant value, and it might do something like this. Okay, and we could even take it one step further. I could do some sort of linear interpolation like so, using linear functions. So you can think of this like, sort of like the rectangular integration rule or trapezoidal integral. I could even do sort of polynomial expansions between them, say. That's okay. So what we're going to do is, for this lesson, we're going to pick out just the rectangular basis functions. So what that is saying is, instead of having this continuous function of linear charge density, we are going to approximate it as little steps of continuous constant charge density across them. And this alpha sub n will just represent the height of that little piece. So you notice it's an, oops, that should be an alpha there. So the idea is, as I chop this up into more and more elements, then the approximate basis functions here will become a better and better approximation to the true continuous value. It will never actually be perfect, and ideally this would have to approach infinity in order to get a perfect approximation, but that's okay. We can eventually truncate it at some point, say, 100 samples, and if that gives me good accuracy out to 10 decimal places, then who cares? I don't need absolute perfection. I just need an approximation that is good enough. All right, so that idea is going to help us simplify this integral a bit. So all we do is plug in that basis function here. So what you'll get is something kind of like this. So it's approximate 4 pi epsilon naught, right? Because we're not going to use the true continuous function here. I'm just going to say the summation from n equals 1 to big N, alpha sub n, u sub n of x prime, all over square root of x minus x prime plus a squared dx prime, like so. Now, so remember, this basis function is going to treat the charge density as if it were constant across each little bit. So the way you write that out will look something like this. U sub n of x prime is equal to a piecewise function. And it's going to be 1 and 0 for, I'm going to write this as x sub n minus 1 is less than or equal to x prime, which is less than or equal to x sub n, okay? And then this will be otherwise. So what are these limits? So you notice I've chopped it up into little bits like so. So I might write this as something like the following. I'm going to call this x0, x1. This will be x2 dot dot dot, x sub n minus 1, and then x sub n, like that. So you notice I've done zero basing to say that there are n subdivisions, but that means there will be n plus 1 edge points here. So each subdivision has 2 boundaries associated with it, like so. So how does that help us here? So that just basically says if I am at n equals 1, then that would imply this little subdivision here. So it goes from x0 to x1 will be a value of 1 for this basis function, and then 0 all the way out here. And then the next one will be out here at n equals 2, so it'll go from 1 to 2, and so on. Okay, and then all the way out to n, which will go from n minus 1 to n, like so. So you imagine this tiny little subdivision like so. So what that does is this integral now becomes a summation. It's going to look sort of like the following. So let's make some room here. Let's redraw this. Okay, so you notice I've rewritten my equation here, and we're going to expand this about this summation here. So how does that work? Well, first things first, this guy is going to break up the continuous integral into a bunch of little sub-integrals. It's going to kind of look like the following. 1 over 4 pi epsilon naught, and then we're going to have a summation out here from n equals 1 to n, alpha sub n, the integral from x sub n minus 1 to x sub n, 1, I guess we'll just say dx prime over here, divided by x minus x prime squared plus a squared, like so. So what exactly does this represent? Well, remember, we still have this thin wire over here, and we just chopped it up into these n little subdivisions, right? So if I pick some observation point out here, it is simply the superposition of all of these little contributions, right? So I have a uniform charge density here, and a uniform here, and a uniform here, and each one of those is a little integral here from that little interval, subinterval there. So I would integrate that uniform density weighted by that coefficient, and all of them taken together will give me my phi of x at some arbitrary observation point here. Technically, except I can't do that just yet. If I had a y there, that would make sense. I could have an x comma y, but we are going to limit ourselves to points just along here. So we're going to write that as phi of x, like so, and then this becomes an a squared, like that. So I've limited myself to points along the wire so that this does not become a variable of y, and that's okay. So So you notice the same idea applies. I just have Coulomb's law adding up all the little contributions. I don't necessarily know what their magnitudes are, but if I did, then in principle, I could carry out this summation and calculate my phi at some point, somewhere, some distance a away from the x-axis. So how is that helpful? Well, we know in particular that this value here is equal to a constant phi naught, like so, okay? So I could pick any arbitrary value x as long as it is between 0 and L, and this equation will be true. So you notice we're getting very close to a system of linear equations. The only tricky part is this giant monster here. So what we're going to do is what's called the point matching method. Like so. And the idea is I know what the scalar potential is all along this. So I'm just going to pick out n values of scalar potential. So I'm going to call this, phi 1 here, and then there's a phi 2 here, and a phi 3 here, and so on, all the way out to p sub n. And they're all equal to phi naught. All right? But we aren't going to quite do that just yet. We know that in our heads, but I'm just going to take one step back and write this as phi sub m at some arbitrary point x sub m, like so. So that sort of makes sense. So I pick a value here, some arbitrary x sub m. Usually there's a lot of flexibility here. We can kind of pick any position we want. But if I have the mth one here, then that means it's going to satisfy this expression here. So that would become a constant there, whereas this is the little integral that I'm integrating over here. So remember, what this represents is there's a little piece of uniform linear charge density on that little sliver here. And then there's another one over here, another one here. And we're adding them all up to find the total scalar potential at some arbitrary observation point there. So why are we going through all this trouble? And the key is to take a note here that this is, if I do this n times, I will get a system of equations, a system of linear equations. So let's write that out in a little more full detail. So you'll have something that might look like the following. 4 pi epsilon naught phi 1 is equal to, we're going to write this as alpha 1 a11 plus alpha 2 a12 plus ... alpha n a1n. And then I could take another sample in my scalar potential, phi 2. So remember, we know these are all going to be the same value, but hypothetically, we don't necessarily know that just yet. So I'm going to leave it as a generic phi 1, phi 2. So this will be alpha 1 a21 plus alpha 2 a22 plus ... plus alpha n a2n, and so on, all the way out to 4 pi epsilon naught a sub n is equal to alpha 1 a sub n1 plus alpha 2 a sub n2 plus ... plus alpha n a sub nn. So I've written it explicitly like this so that it's clear that we have n equations with n unknowns, but in reality these are all the same value, phi naught, like so. All right, so what is this matrix element here? We just write this as a sub mn is equal to the integral from x sub n minus 1 to x sub n dx prime all over the square root of x sub m minus x prime squared plus a squared, like so. So you notice we've come back full circle to this idea of a system of linear equations where I know the scalar potential at n different locations, and I know the kernel as dictated by this matrix element here. And the only thing that's fundamentally changed from our last discussion is, you remember last time we assumed that each of these contributions was a bunch of little point charges. Well, now we're just saying, well, let's suppose each contribution is a little bit of uniform linear charge density. So instead of getting just a simple 1 over the magnitude of r minus r prime, you're getting really this integral over this constant value. And that's kind of the essence of the method of moments, is that you can expand it to more general expressions of contributions, right? So our initial assessment, this would assume little tiny point charges. This is now little bits of uniform charge density. And if we used higher order basis functions, then this integral here would change a bit, but this underlying structure out here would be exactly the same. So the value of your approximation using the method of moments depends heavily on how you chop it up into tiny little manageable chunks. All right, so part of the reason why we chose the uniform charge density here is that this integral has a closed form solution. It doesn't have to. In principle, remember, we're all experts in numerical integration. So we could have put in any arbitrary basis function we wanted, and then we could calculate this to any arbitrary degree of accuracy, just using Simpson's rule, say, and that would have been fine. And that's one of the powerful beauties of the method of moments is this integral doesn't even have to be evaluable in closed form. It doesn't have to have a closed form solution if you don't want. You can always evaluate this thing to any arbitrary degree of accuracy. And in fact, that would make an interesting final project, is to take something like this and use higher order approximations here for your basis functions. And even if you can't evaluate this thing exactly, you could use numerical integration on each one of these little matrix elements here. But we've deliberately chosen something here that has an exact solution. And part of your homework will be to actually prove this. But this actually has a closed form solution. And it looks kind of like this. So I'm going to replace this with x sub a. And then I'm going to call this x sub b. And you notice there's an x sub m over here. All right, so let's write that out. X sub b minus x sub m. And there's an x sub a minus x sub m, like so. And then it is plus the square root. Oh, I'm not falling off the edge here. X sub, excuse me, x sub b minus x sub m squared plus a squared, like that. And there's a x sub a minus x sub m squared plus a squared, like so. All right, so your job will be to derive this from here, but the fact that it exists means you don't really have to approximate this integral. You can calculate it exactly. And yeah, it's big and it's ugly, but who cares? MATLAB can crunch on this without any trouble at all in a matter of microseconds, so what? All that matters is we know that this thing exactly evaluates this integral, and so we can then evaluate all of these little matrix elements. And you eventually get our familiar matrix vector equation that'll look something like ax equals b again. And then to invert this, you just calculate x is equal to a inverse b again, just like you did before. So nothing has really fundamentally changed as far as your code is concerned. The only thing at the end of the day that changed was these matrix elements. Whereas before, these were just 1 over distances. Now they're going to represent these integrals, which is just a fancy way of saying instead of squishing all of these charges into tiny little discrete points, we are spreading them out a little bit as uniform distributions along this wire. So instead of having the kernel for little point charges, this is the kernel for a little continuous sectionally constant charge density, a linear charge density. Now, when you do this, there's also some things to beware, is that we've made some approximations on top of approximations. So what'll happen is you can chop this up into 20, 40, 50 pieces, and you'll actually get very good answers out of it, but you can't do that forever. And the reason is because we have two sort of conflicting approximations here. So the first is that we assumed all of that charge density was squished down along an infinitely thin wire, but then we imposed the condition that the scalar potential was constant on the edge of this cylinder. So those are kind of contradictory assumptions there. And if you chop it up into too many subdivisions, you'll actually start getting greater error as a result of that. And that's just the price we paid because we wanted to force this situation into a manageable expression. So what you'll find is the method of moments here is going to work very well up to a point. You might do something like n equals 50, n equals 100, n equals 200, but if you go beyond that, all of a sudden it might blow up. And it'll depend very strongly on just how much that thin wire approximation holds. So remember, there is some radius here, a, and we need that A to be very, very small. So A is much, much less than L. So the better that assumption holds, the better this method is going to work. But if you're not careful, if that assumption is not so good, then you cannot chop it up into progressively more subdivisions and expect your results to get more and more accurate. So you'll see that in the homework. You'll get a very good answer for the most part. So what you should see when you actually carry this out is you'll plot something like the following. This will be my L hat, my estimate for the linear charge density going from 0 to L. And it'll do something kind of like this. So you'll have some sort of baseline charge density here, and it will want to sort of shoot up to infinity at the edges, like so. And what's happening again is all that positive charge wants to sort of repel itself towards the edges. And the more finely you chop this up into little bits, the better that approximation gets. But if you do it too fine, then because this approximation isn't perfect, you'll eventually start getting weird little bits of error where it does this sort of thing, like there. And that's just the fact that we made some certain assumptions here that we can't push forever without causing our model to kind of break down a little bit. So we'll explore that a little bit in our homework project, but that's essentially the result you should get. So if you see something that more or less looks like this, this happy face, this smile going up, then you know you've got the right answer for your inversion method. So good luck.